My name is Ruth, and today I will be discussing a fundamental principle of physics, Newton's second law. I will show how the computer uses iteration, the repeated use of Newton's second law, to predict the motion of an object moving at constant velocity. I will then compare this computer model to the results obtained by observing and analyzing an object moving at constant velocity in real life. First, I want to make sure that Newton's second law is understood, as that's the key physics principle used in this experiment. The equation for Newton's second law can be seen here as the change in velocity over the change in time is equal to the total forces or net forces acting on the object divided by the mass of the object. Some simple algebra can be used to put this equation into a form that will be more useful for our experiment. First, we just multiply both sides by the change in time. Then we remember that the change in velocity is really just the final velocity minus the initial velocity, and we use that to get the form of the equation that you can see here, and that's the form of the equation that we will be using in this experiment. It's also important to remember that in this experiment, the total or net forces acting on the object is equal to 0, which makes that entire term equal to 0. So really, what we're saying is the final velocity is equal to the initial velocity. In other words, there's constant velocity, which makes sense for this experiment. By the same logic, we can obtain the equation of the final position, shown here. This will also be useful later on. Next, I will look at the video recording of an object in motion and discuss the program that was used to analyze said motion. We see that we have a standard size basketball, which is why we set the calibration stick to 0.24 meters, which is the diameter of a standard size basketball. Now we'll play the video. You can see that over here a table as well as a graph is created to plot the points as the ball moves across the screen. One important thing to note is our axes. We can see that if we flip these axes, we suddenly have a graph that has a positive slope. This is because we have now flipped it so that the ball would be moving in the positive x direction. If we flip the axes back to the way that they were originally, we have a negative slope because these are the axes that we see normally, with positive x to the right and negative x to the left, which is the direction that the ball is moving. Now let's look at the code that was used to create the computer model of this basketball motion. The first thing to notice is the ball's mass, which in SI units is equal to 0.567 kilograms. The ball's initial position is taken from the initial x value of the ball, as shown in this table. The ball's initial velocity is found by remembering this equation. Velocity is equal to change in position over change in time. The values of the first 2 points in our table were used to solve this equation. Both the initial position and initial velocity are put in vector form, and the initial time is set to 0. The calculation loop from the code is enlarged here, as this is the most important part of the code in terms of examining how the computer uses Newton's second law to predict the motion of basketball. This loop is only in effect while the time is less than the final time in our video. Also, the total forces acting on the ball are set equal to 0 because it is moving at constant velocity. Now we get into Newton's second law. Here in this line and also in this line are the equations that we derive from Newton's second law, seen here and here. Now let's run the code. We see that the model and graph obtained look like the observed motion of the basketball. But to check this, I'm going to create a graph using Google Spreadsheets. We can see that the data obtained from the model and the data obtained from the experiment line up pretty well, but there are some irregularities. These irregularities are caused by factors that were not accounted for, such as slight acceleration, friction with the table, or even just human error. If I had been even more precise and all other factors had been eliminated, the graphs would have lined up perfectly. In conclusion, we learned from this experiment that iteration, the repeated use of Newton's second law, It's a good way to predict and model the motion of an object moving at constant velocity.